So, it is like this. Let us come back to the real case. Every day, I begin the class with a diagram like this, because this is my reference. But today the weights will be written in a vector form. You can either write W n or W transpose n. We have so far proved convergence in mean. I am not going to repeat that part, because that we have considered extensively. We have first dealt with the real valued filter weight case, then extended to the complex valued case, and we have seen that as time tends to infinity, n tends to infinity, the iteration index tends to infinity. I mean the mean of the weight vector, because weight vector is every component is fluctuating, is random variable, but the mean of that coincides with the optimal one as n tends to infinity, provided you choose the step size within a limit, from within a limit. That is, mu should be greater than 0 and less than 2 by lambda max. Lambda max is the maximum magnitude eigenvalue of the input autocorrelation matrix. And then we derived the easier but stricter bound from that 2 by trace r. Lambda should be, mu should be less than 2 by trace r. That is what, that is true for both real valued as well as complex valued cases. But as I told you, that if it had it been a proper pure steepest descent search, the weight vector indeed would have coincided with the optimal one exactly. But I represented, I replaced R matrix by a weird estimate, just x n into x transpose n or x n x Hermitian n. So did I for p vector, there is just x n into d n or x n into d star n depending on the case. Okay. So obviously you are paying a price, you are not finding the weight even at n equal to infinity or very large n, weight is not stationary at the optimal one, it is still fluctuating. And as a result, if you find out that filter error E n, even in the steady state, that is called steady state, when n tends to infinity, actually not infinity, when n takes very large values, we call it steady state. Even in the steady state, that is when indeed it has converged, that is the steady state means when indeed the mean of the tap weight vector has coincided, is giving you the optimal one. That is a steady state thing. So, it normally takes 500, 400, 300 iterations, depending on the case. So, that is a steady state. So, even in the steady state, you are not getting exact optimal weight vector here. You are getting still a fluctuating quantity, which mean is optimal one. As a result, the E n that you have here will never be the one which has the minimum variance, because we wanted to find out first the optimal filter weight by minimizing the variance of this, and we got the winner filter and all that. Now, under the present situation, if you take the variance of E n, you are obviously you will not get that minimum mean square quantity here, minimum mean square error. There is the error which gives rise to minimum variance, because you are not putting the optimal weight exactly, you are giving a fluctuating quantity whose mean is the optimal one. But W transpose n or W n is not equal to optimal one, okay, always, right. So, then the question is, how much is the deviation, how much do we lose in terms of the error variance? So, you can intuitively see that if the tap weights are such, the filter weights are such that around in the steady state, around that optimal value, they are fluctuating, but fluctuating in a very narrow range, that is their spread or variance of each tap weight around the mean optimal value, okay, is not much. So, obviously, this E n will be a better one, that is its variance will be closer to the minimum variance that is attainable. In fact, if the tap weights are such that they are fluctuating in a very, very narrow range around the mean, this will be indeed almost at least asymptotically the optimal error, in the sense that its variance will be nearly minimum. On the other hand, if the tap weights are such that okay, the mean is fluctuating in the steady state, but mean is as guaranteed by your convergence analysis, mean is this optimal weight vector, but its range of variation, spread or variance around that mean is really very large. So, obviously, that will reflect on E n. If you compute the variance of E n, that will have much deviation from the minimum variance that was attainable. So, these two are related, of course. So, we will just do an exact analysis, okay, because we want to keep that extra component, the spread of the weight error in the steady state for each weight, each filter coefficient or each weight under bound. Okay. So, then let us start with this. In fact, this is a bit of repetition, because towards the end of the previous lecture I did this. So, I as you know, my practice is to always take up from the last 5 minutes of previous day's lecture and then continue. Okay. So, E n is as usual, and I am doing this analysis will be done purely for a real valued case. For complex it is more complicated, doable but very clumsy. So, we will not do that. So, d n minus w transpose, these definitions you all know. What is x n vector? I do not have to tell you. It is a tap weight vector that goes from 0th to capital Nth. So, n plus 1 components, and you all know this. We know that W opt is R inverse P, and we define the definition W n minus W opt was our delta n, is not it? These are all known. So, if you replace W n by W opt plus delta, if you replace W n by W opt plus delta n, then you can write this error as E O n minus, where E O n is what? The one which you would get with minimum variance, that is when you really put optimal filter weight here, W opt here, then the output is W opt transpose x n vector, error is d n minus that, which is E O n, that is E O n is d n minus W opt transpose times x n vector. Okay. So, ideally I would have wanted this, but this deviation is causing this problem. So, let us see its effect. And as I tell you that as we go through this lengthy analysis, you will also learn some techniques of how to do manipulations, how to simplify things in statistical analysis. That is one major objective of this course. It is not just adaptive filter understanding and derivation and all that. This course will give a solid training on statistical analysis of signals and systems. Okay. So, that if you find this kind of things in other contexts, communication and control, system analysis, you will not find difficulty. You are used to this kind of analysis, whether you are reading a paper and all that. It is not just adaptive filter theory that you want to emphasize on. Okay. So, if you take the variance is square of this is a scalar. So, a minus b whole square equal to that a square minus 2a plus b square thing, and apply expected over this. Okay. So, this is your another definition. Epsilon square was the minimum variance. Huh? Is it okay? No, was going beyond or what?
No, you are using this camera, not that.
Oh, okay. Thank you. So, this we know. Okay, that was the minimum variance attainable, epsilon square. In fact, you can write epsilon mean square. Okay. And obviously, we are not getting this. So, what we are getting? I am calling it epsilon square n, because after all, it is a function of n. As n tends to infinity, it can be independent of n, but in general, a function of n. So, that will be what? Square it up, square of this quantity, that a minus b whole square thing. Obviously, one term will be coming from this, which will give rise to epsilon mean. I am not doing those steps, is not it? Square it up means square it up, a square, a minus b whole square, so a square, expected value of that will give you epsilon mean square. Okay. This square is part of the notation. It indicates that the quantity is of is a second order quantity. When I put a square here, just to this 2 is nothing, it is just part of the entire notation. It just reminds you that the quantity that it represents is a second order quantity. This is square. Pardon me, epsilon square n. Oh, this is E, sorry. This is E, I am sorry, this is E. Thank you very much. Yeah. So, this will be epsilon square mean minus twice E. A B or B A both are same. So, delta transpose n I write x n. So, this is a scalar. row vector, column vector, scalar, this is scalar. So, minus 2ab, a and b, or 2ba, both are same, a and b are scalar. So, I write this way. Plus E of this quantity, square up this quantity, this. Squaring up means I can repeat it, and why repeat? You can, you know, the transpose of a scalar is same as the scalar. So, I can repeat this. So, I am not showing those steps, just hear me out. I have to square it up. Square it up means this multiplied by itself, or this multiplied by the transpose of itself. Okay, because scalar and its transpose, they are same. So, that means first is delta transpose n x n, and the transpose of that. So, that will bring back x transpose n here and delta n. Now, look at this. Here I made that weird assumption which works very well in practice, that is independence assumption. Independence assumption was this, I repeat again, since this is a very key thing, you can say key weakness in the LMS algorithm analysis, okay, is that we assume there is independence assumption there are some recent research where people try to avoid this assumption, make some other analysis. There will be some progress in that, but not to this extent. That is called deterministic convergence analysis, very recent work actually, last 3-4 years. Because this assumption is kind of, you know, I mean, with, it makes us feel a bit uneasy. But it assumes that Wn is when I say independent, I am writing here statistically independent, but in future when I say independent, I would mean statistically independent, unless I specifically say they are linearly independent. There is another independence and dependence, defined context. But when I talk of random variables being independent, I will usually imply statistical independence. That is, the joint probability density is a product of individual probability densities. Okay. So, statistically spelling has been wrong. So, I am writing SI, statistically independent of what we assume, current weight vector and dn. Now, you see, I see that this is not a very good assumption technically, because what is Wn? If you see, if you apply the LMS algorithm, instead of n plus 1 on the left hand side, if you put it n, so it becomes n minus 1 here, plus mu into x n minus 1 vector E n minus 1, isn't it? This is your LMS algorithm. You see, Wn depends on x n minus 1 vector, but that vector and x n vector has got overlap in fact almost all the components except for 1 or 2. Okay. So, that means Wn has some dependence on x n, and this E n minus 1 depends on d n minus 1, d n minus 1 minus the corresponding filter output. So, this depends on d n minus 1, but d n minus 1 and d n, they may be correlated. It is not that there is a white process, they will be correlated. So, this also has got some correlation with d n, isn't it? So, it is not a very good assumption, but then it possibly works because they say that, you know, this product is less and then mu is also is less. So, this contribution is less and all that. That is how they try to build up an argument, but this works very well in practice. How it works, we do not know. Experimentally, it has been simulated, it has been tried so many times. We have done it so many times, we implemented. We do it regularly, in fact, here in various contexts. So, it works. So, there is some other thing I do not know which is inside. So, that is why people are still doing research to find out more effective convergence analysis and all. So, this assumption I make. Okay. If I make the assumption, then that means why only Wn? Delta n. What is delta n? It is Wn minus W opt. W opt is a constant quantity. So, if Wn is statistically independent of these two, so is delta n, isn't it? So, is delta n. So, delta n is independent of x n, dn, and EON, again EON depends on what? dn and x bar n. This is constant. So, I can say this guy delta n is independent of both this, because this is x n and this again depends on d n and x n only. So, this is independent of these two. I did not use the assumption of uncorrelatedness. I told you uncorrelatedness does not work here, because uncorrelatedness of two random variables x and y only means E of x y is equal to E x into E y. But you cannot say if they are uncorrelated, then E of x square into y equal to E of x square into E of y. That kind of thing will be here. You see x n, and this also has x n component. So, it will be product, square terms of x will come up, isn't it? That times this. So, you cannot just simply assume, make use of uncorrelated assumption. You have to bring in statistical independence, then only you can separate out. Then you can separate out this part E over that, this part E over that. Okay. But what does that mean? That is, this term, if I write this way, this term gives rise to E of and what is EON? EON is the error for the optimal filter. EON is the error for the optimal filter, and then EON is orthogonal to each component of x n. We have proved it, isn't it? You remember we also proved it. We not only talked based on analogy, or do you want me to do this again? EON, whether you put it before or after does not matter, okay, because this is scalar. That times each component, if you take the product and expected value, there is a correlation, which was that dot product or inner product, that this is 0, because this is the optimal one. This corresponds to the optimal filter. That time this error corresponds to orthogonal projection, that is d n is orthogonally projected on the space spanned by x n minus 1 up to say x n minus capital N. Which first term? This one? No, that. But I have not pushed good. That for few seconds I thought so earlier, but then I realized that I have not pushed n to infinity in this analysis so far. It's finite. I mean, I am not into steady state. Na? I am trying to find out the expression at any general n, not necessarily on convergence and all, and then I will slowly let n tend to infinity. What you are doing is you are going before, you are substituting the limit before at the beginning only. You understand? So, I cannot do that. Only in the steady state after convergence its mean is 0. That is why I am not touching that. Okay. You cannot assume that limit at any finite n or okay. Before I make the limit n tends to infinity, you cannot put the limit here. But this is 0 then, right? This gives rise to 0. Okay. We have proved it in some of the lectures earlier. So, we are left with only this term and this term. You see, this is a positive term, you can see a square minus 2ab plus b square. So, b square is a positive term, a square. So, that is why this extra contribution comes. I would have been very happy if I had only this much, but you can easily see some extra terms is coming, isn't it? So, let us see how much is this term. Okay, you can see one thing, please look at this vector delta transpose n, x transpose n, delta n, and E before that. How to analyze it? Only thing I know, delta n is independent of x n. Only thing I know. Before I do that, here you learn some trick in statistical analysis involving matrices and all, especially. But before I deal with matrices, think of this. Suppose I have got two quantities x and y. X and y are statistically independent. X, y, s I. And you are finding out E of f x is a function, y is g y is a function. Obviously, f x also and g y they are also independent. It is coming purely from x, this is coming purely from y, so they are also statistically independent. So, we know this will be simply this E of f x into, isn't it? Because you multiply by joint density is separable, two different integrals, two different means and product. But this is a scalar quantity. This is a constant quantity, non-random quantity. So, suppose I take it this way. This I call say mu g, this I call mu f. So, it is mu f into mu g, isn't it? Don't I get the same thing if here I bring in E on this? Since they are separable, aren't these two same? Mu f into mu g, E g y is mu g is constant, goes out. and then I am left with E f x, which is mu f. Since they are separable here, I can do that. You cannot do otherwise. Since they are statistically independent, separable, please see this trick. This is the basic, and then I will extend it to matrices. Are you following this? E f x g y, ordinarily you cannot do that. But if they are separable, because the moment you apply E over it, it no longer remains random. It goes out. But that is only possible only if these two are separable. That is, after application of E directly also they could be separated. That is, this has no, I mean, you see, this can be done separately, this can be done separately. In that case, you can do that inside the outer E operation. Okay. Now, suppose you have got two vectors. Instead of x and y, say two vectors x and again x and y are two mutually statistically independent vectors. They may be, these two may be not independent, these two may be not independent with each other, but x and y are two different things. They are statistically independent. So, any x1 with y1 or x1 with y2, x2 with y1, x2 with y2, they are all statistically independent pairs. Suppose this is given to you, they are SI, and suppose you have got things like this. In fact, instead of going directly to the result, let me do some exercise. This, my claim is, can be written as y after all. What is x transpose y? Please see, I am taking you step by step to some main result. What is x transpose y? If you want to do it directly, x1 y1 plus x2 y2, on that you will apply E. So, since x1 y1 they are independent, you will get Ex1 into Ey1, Ex2 Ey2, like that, isn't it? But if you take that Ey1 or Ey2 some constant, call it mu y1, mu y2, it is like mu y1 into x1, mu y2 into x2, and then you apply expectation. It is the same thing. Are you following me? What do you get here? E of y1, I am writing it as it is, not mu y1, into say mu x1 plus E of y2 mu x2, isn't it? So, it is like E of y1, or maybe the other way, E of x1 mu y1. So, it is like E of this vector times mu 1 mu what, mu y1 mu y2, which is again E of y1 y2, isn't it? Huh? You will get the same thing. You understand please understand the trick, that is, you don't do this work, I will do so much and then verify. No, please see the core of it. What is the thing is, they are separable, that is why it is working. These two are separable, na? So, whether you do this expectation beforehand and then do this multiplication and expectation, they will then appear as constants, or you first multiply and then do expectation, you will get the same thing, because they become separable. Huh? No, I am just showing a result. Why don't you, this is only an intermediate step. This is true or not? You have understood the trick here? Okay. Now, I make it slightly more complicated. Suppose it is x transpose y transpose x. Then my claim is this is same as E, this will remain as it is. You can apply this on this. To get this result, I made you prepared through that previous result. Okay. You see this. This is a, I mean, suppose you want to do like the conventional way. So this is y transpose is a matrix. Y had y1, y2. So this will be y1 square, y1, y2, y2, y1, and y2 square. This is this matrix, 2 by 2 matrix, and then you have got x1, x2. Please see that, actually, please try to understand what is happening inside, so that I mean, you come across similar cases and you yourself can tell me what will be the result. Either you do the entire product and then apply E separately, but if you do the entire product, say one term y1 square, after all this into x1 plus this into x2, that times x1. There if you apply E, y1 square, that can be separated out. Maybe I worked out from one term, say y1 square into x1 and y1 y2 times x2, that will be the first component of this product vector, that with x1, isn't it? So that with x1, one term, plus another term, E over this is separable. So I can take E on this. This is as good as E x1, E y1 square x1 by previous arguments, okay, plus E y1 y2 x2 plus the other term. Can I do that? Huh? So what is this after all? It's like if you apply E over this matrix, E y1 square times x1 into x1, okay, E y1 y2 times x2, isn't that this? Please see what I am doing. I mean, in case you want, if you want, I can repeat. Have you understood this? So this simple technique. Is that, so do you have to explain further? So this I can do, though this is enough for me, but just to tease you further, suppose I have got a situation like this: x vector, y vector, z vector. You have got a situation like this: say, y, z transpose. So this is a matrix. Say y, something like this. Y z transpose is a matrix, isn't it? Y z matrix, that times a column vector. So column, row, column, something like this. Here, for God's sake, do not make it E of x transpose E of y, z transpose E of y. This is not correct. Okay. In general, not correct. Can you see this, or no? If y itself is okay, uncorrelated, what this is equal to by our previous logic is E of x transpose into E of this part. This is always true, if provided z also is statistically independent with x, so that the entire thing can be separated out. Provided z also is statistically independent with x, then this can be done. But then this you cannot separate out, even if suppose z is statistically independent. Suppose z is statistically independent with y. You cannot write, it's like the y1, y2, please see this, z1, y1, y2, z1, z2, and again y1, y2. So understand there will be some square terms, z1, y1 times y1 square and all that, and expected value of that. Even if Z1 and Y1 are statistically independent, you will get E into E of Z1 into E of Y1 square. E of Y1 square is not square of E Y1. That is what you will get if you apply this here. Follow me? One E of Y1, Y2 would come, E of Y1, Y2 would come, and their product will come up. Not that of E of Y square, but E of Y into E of Y, that kind of thing. So please, whenever you are in doubt, just take 2 by 2 case and all that, and okay. So now I come back to that. What was my contention? I was here. This fellow became 0, I am here, and here obviously you see delta n, I made the assumption that this delta n is statistically independent of x n. That was my independent assumption. In terms of W n or delta n, both mean same, but delta n is W n minus W opt, isn't it? W n minus W opt. So delta n also is statistically independent of x n. That is the assumption. However weird it may appear to be, I have made it. So I can apply that logic. E of this entire thing means E of same with E coming between x n and x trans, coming before x n into x transpose n. That is, what is that? I am repeating again. What we got here is epsilon square mean plus E of delta transpose n. Then we had x n, x transpose n, delta n, isn't it? This would it. I can say, since they are statistically independent, by your assumption, you can apply the E over this, and this is your R matrix. Okay. So E of delta transpose n or delta n. R is a matrix, delta is a column vector, so product is a column vector, row into column, scalar. Now scalar and its trace, they are same. Please see the tricks we apply, to simplify things. So this is same as E of an expected value of a trace, and trace of an expected value, they would be the same. Take a square matrix, take trace and then E, or take E and then trace. After all, trace is sum of diagonal values. So we apply the expectation, then take sum of the diagonal ones, or sum of the diagonal ones, and then E, you will get the same thing. Suppose E of trace, I take the trace of this guy to start with, trace of this entire thing, this thing. Okay? And you have seen trace of AB is trace of BA, isn't it? Suppose this delta transpose n into R is your A and delta n is B. Suppose delta transpose into R, this part I call A matrix, and delta is B. So that means it is same as trace of delta transpose into R. Okay. And this trace, okay. So this is trace of still this is a scalar quantity only. Delta transpose is a matrix, matrix into matrix, trace of that. Trace is scalar. Okay, and expected value of trace or trace of expected value, they are same, I told you. So now what I do, I take trace out, put E in, and remember R is not random. So R can be taken outside the E operator. R is constant, no longer random, isn't it? So matrix into matrix, you multiply and take E, or take E on this and then do the multiplication of the matrix, you will get the same product. This is a matrix which is non random, which is constant, not random. This is a matrix. You first multiply and then take E over each element, or you better take E over each element and multiply by, you will get the same thing. Please use your imagination. So that means I get into R This matrix, I give it a name K n. What is this matrix? What is delta n? Delta n consists of the tap weights, the tap weight error, vector. Tap means filter coefficient. Tap weight or coefficient, they are all equivalent terms. Sometimes we say tap weight, sometimes we say filter coefficient, sometimes just weight. The books call it tap weight error vector, that is error from the optimal one, okay, which is again a random quantity. So, this quantity, if you take its, so this into its transpose. Okay. So, what will this be called? Weight error covariance. Actually, it should not be called covariance, but as n tends to infinity, that time at least delta n has got 0 mean. So, correlation and covariance, they are same. So, keeping that in mind, they call it tap weight error or weight error covariance matrix. So, you understand, as n tends to infinity, we have to see what becomes this, but essentially whatever it is, you will get an extra component which will get added to this. You will never get this alone. Okay, you will never get this alone, because delta n is, I mean, this is not becoming 0. This is because delta n, its mean is 0. Weights only fluctuate. It does not become exactly equal to the optimal weight always. Isn't it? So, you will have this is a non-zero matrix, that times R, and then take trace. So, some quantity will come up. Question is, this quantity should be kept under some bound, and that bound should be under our control by some parameter. Okay, that is why we will analyze this quantity later. Okay, but you understand, if this quantity becomes larger, naturally it is a bad one. We are deviating much from here and vice versa. Okay. And what is
How does one think of applying the trace at that point? Like
trace into K n into R?
No, means in second line.
Second line, that's why trace is taken actually.
Because then I could make use of the fact trace of A B equal to trace of B A.
No, sir,
Means,
actually,
why you
from
thought
E,
that
we are
to
directly
take that
adding E of trace. From E, we are directly
E,
adding E of trace.
and this is a scalar quantity. Scalar quantity and its trace, they are same. So, you will permit me to bring in a trace there. Trace of 2 is same as 2, trace of 5 is same as 5.
Sir, I am not asking why this is right. I am asking how will we know? I mean, is this a general method of proving or?
No, I am got this result. Through this process, you learn some trick. That way, how suddenly trace can be brought in.
Why will we bring in trace?
Because I wanted to bring in delta from rightmost to leftmost. Then delta into delta transpose, they come together, and I apply E over it. R gets separated out because it is constant.
Sir, then in this case also we can directly, can't we take R out?
How? No. Good question. Think of it. You have got something in the this side delta transpose n or delta. Okay, if you apply E over it, all terms get mixed up. How will you take R, push R to the right side?
That is not possible.
That is not possible. Please think, good that you are thinking. These are the things I want people to think. It is not doable there.
Sir, hence
You want to take R out and delta transpose into delta, is it? I mean, dimensionally that is not such. What is it?
So, as the quantity was scalar, hence the trace concept was applicable.
No, that is a separate question. You understood, or please do little bit by yourself. Okay. But I brought in trace so that delta could be brought in the beginning, using the fact that trace of A B equal to trace of B A. And then I can happily push R out, and I get a covariance term here. This covariance matrix, what is significance if you take the diagonal elements? I am primarily interested in the diagonal. What are the diagonal elements? Diagonal elements will be the variances any covariance matrix, okay, cross terms are the correlations, not correlation, covariances between various components, but the diagonal entries, they are real, here positive, okay, they are the variance power that I should look into, that tap weight error for each tap coefficient, its variance around the mean, actually variance, that should be under control. So, diagonal entries are very important. So, in this case you can see not only diagonal, all the entries are important, that is how it turns out to be, because this entire matrix to be multiplied by R and then trace has to be taken. So, not just diagonal entries. So, this gives an exact dependence on k n of exact actual epsilon square n. So, its value in the steady state means limit n tend to infinity here, this remains as it is, limit n tend to infinity, this have to analyze how does it behave as n becomes larger and larger. Now, to make life further simple, instead of dealing with this, what we do? We replace now R by T d T Hermitian, where you know T consists of the eigenvectors orthonormal, that is orthogonal, and each has norm unity. D consists of eigenvalues which are real, positive, because I am assuming positive definite matrix, and then that means T is unitary, T T H is T H T is I. Okay, and what was and instead of delta n you define this quantity. And instead of x n you define this quantity. Now, what is covariance of this? What is this? Instead of I am writing Hermitian here. You understand why I am writing Hermitian? Because if the eigen, this is in fact there is no need, I can write transpose, because if eigenvalues are real, guaranteed to be real, and our matrix also has real terms, then they all eigenvector components also have to be real. In general, any real matrix does not mean that eigenvalues are real, they can be complex. In this case, since these eigenvalues are given to be your real, because this matrix is Hermitian, real and positive, matrix itself consists of real elements, because I am considering real valued data only. Okay. So, if R is real and D is real, then you know how to compute eigenvectors given. So, you will get a solution in terms of real valued numbers only. So, this will become simply transpose, but in general they are complex. Okay, it's transpose. So, what is this quantity then? You replace this T transpose delta n T transpose delta n and delta transpose T, take T out, T, these things you should be able to do very, I mean by now you should be pretty conversant with this kind of manipulations. Okay. Are replaced by T, T transpose this, and on this transpose T will go to the right side, T transpose comes out, T comes out, delta delta transpose, and delta delta transpose E over that is K n. So, this is T transpose K n T, one thing. Okay. And what is the variance of this? I won't tell you, this is something very simple. In fact, it will be a diagonal matrix. T transpose X, X transpose T, T transpose X, X transpose T, E over that. So, E comes in, X, X transpose is R. So, T transpose R T, that is equal to D. If you multiply T transpose here, here T transpose T cancels. If you multiply T here, T, this is a very standard tricks. You decompose R like this and then take the T transpose, takes apply T over that X, T transpose X, that becomes X prime, that has got diagonal, that becomes uncorrelated. Its correlation matrix is diagonal given by D. This you should not forget. I will do it frequently. This kind of decomposition, immediately multiply T transpose, take the X, pre-multiply by T transpose, you call it X prime, that will have correlation matrix equal to D. So, components will be uncorrelated. This is a very standard in communication control signal processing. This kind of whitening operation, that components become uncorrelated means like a white signal. White signal has got uncorrelated signal, isn't it? Then only power spectral intensity is flat. This is called a process of whitening. There is term, I don't know whether you come across this term whitening filter and all that. In fact, this is, have you come across this term Karahuman-Loeff transformation, KL, in compression and all the first transform they teach you is this, that take X, this correlation matrix, go get this eigen decomposition, T transpose times X, that will give you what at X prime, which will have uncorrelated components. Okay. Earlier you have got components which have lot of correlation, so lot of redundancy. You remove the redundancy, make them uncorrelated, and now see who has higher variances, take only those, throw away others who don't have high variances. That is how you achieve compression. Now, the problem with this transformer is that you have to do this eigenvalue, eigenvector eigenanalysis, which is very computationally expensive. You cannot do it real time. So, they approximate it by DCT. That is why all these JPEG and all that, where you use DCT come in. They try to asymptotically approach this, but this is called actually KL transform. Let's decompose, get into this eigen decomposition, take T transpose, multiply your data vector with that. That is a transpose. In fact, T transpose consists of rows which are orthogonal, that each row times the data vector will give you one component. It is like those rows, or if you see them as columns, they become new orthogonal axes. New orthogonal axis in a n-dimensional space, you try to find, give in a data vector, you have to project on each component and find the components. Those components are uncorrelated. That is KL transform. I am deviating, so I cannot, I am not speaking much on that. Okay, KL transform. Karahuman, all compression books will start with this first. You must have come across KL transform, isn't it? This is KL transformation, nothing else. So, this will have, I can write D. You are agreeing or not? I am not doing all those steps. Huh? This is D. D consists of the positive real eigenvalues of R matrix. Okay, now, if I apply these definitions here, now trace of K n R. Please see R I want to write as T D T transpose. Okay, and then apply that theory. Now, do not see it, look at it as K n into T D T transpose, trace of that. So, trace of A B is trace of B, I will apply again. This will be T transpose is my B. Now, T transpose I will take as B, the remaining ones K n T D as A. So, obviously, T transpose will come here next time, T transpose K n T, and what is that? The variance of this guy, which you can call K prime n. Are you following me? I will apply that thing, trace A B is trace B A. This is my B, T transpose, K n T D is my A. So, trace of A B is same as trace of B A. B A means T transpose, you see T transpose, K n T. This part I can call K prime n and left with D. So, that thing will be trace of K prime n into D. Okay. And now, what is K prime n? If you multiply, please see this is a diagonal matrix. You are multiplying a square matrix by a diagonal matrix post multiplication. What will be the resulting matrix? First column of this will be multiplied by lambda 0, second column by lambda 1, I told you how to do matrix multiplications, please remember that. Linearly combining the columns by the respective elements, row elements. This is a diagonal matrix, this one lambda 0, lambda 1 dot 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 lambda n. This has 0 0 0. Take this first column. By these elements you have to linearly combine the columns of these, but these other elements are zeros. Other elements are zeros. So, only the first column will be multiplied by lambda 0, the second column by lambda 1, like that. After that you are taking trace. So, 0 0th element means lambda 0 has come there, 1 1th element lambda 1 has come there, 2 2th element lambda 2 has come there, isn't it? So, that means this is nothing but summation this matrix ith diagonal element times lambda I. So, even here you can see if this quantity is bounded, if each term is bounded as n tends to infinity, then this will be under our control. You cannot make this 0, eigenvalues are not all zeros, then there is a peculiar process, process which has all, which can take only 0 values always, because variances are zeros. Okay. So, that is not the case. There will be this term always. You have to see how this behaves as n tends to infinity. What happens to this quantity? That is something you have to bear with. Now, how to keep that minimum? That is what you have to see. That means I have to study these quantities. Okay. So, what is KII? I just repeat, this will be the most very elaborate analysis spanning possibly 2 days or 1.5 days. What are these quantities? They are coming from this K prime n. What is K prime n? K prime n was your T transpose K n T, that is E of delta prime n, where delta prime n was T transpose delta n. This quantity figures here in terms of its diagonal entries. We will study this quantity, how it behaves, this matrix as n tends to infinity. That means, I have to substitute all this delta prime by T delta n and all those things here, okay, and do some analysis. So, that is a very lengthy, though interesting. By now, you are prepared for it. Some other tricks I have shown, they will be repeatedly applied here, there, here, there. So, please apply your mind before coming to the next class. Okay, thank you very much. Okay, yeah, anything? Yeah, you want this? So, the class is over. If you have any question, you can ask me, because I see they have not switched it off yet.